All right, let's hit 4.5 really quickly. So we have exponential growth and decay. So the good news is that we've already been doing some growth and decay. The population thing we just did, that was growth. Whenever we're investing money, that was growth. The decay one I don't think we've done yet. But we've at least been working with the same ideas already. But now we're going to call it a different section. All right, so this looks really horrible. So f of t equals a naught times e to the power of kt, and it's going through and telling you if k is greater than 0, it's growth. If k is less than 0, it's going to be decay. The easy way to think about it is whenever we had the compounding continuously, this is the same idea. With compounding continuously, our rate was always positive. So we were always doing growth. So whatever our r was is kind of the same idea as what our k was. K is your constant that's going to help, that represents the growth or the decay. Do you guys remember doing direct and indirect variation? All right, well I got two yeses. Whenever we were doing direct and indirect variation, we would have y equals kx and y equals k over x. Where the k was just a constant of variation. This is the same idea where k is going to be a constant of growth or decay. Anyway, the little beige rectangle looks really horrible. It's really not bad. So we're just going to jump in. All right, so here we have the exponential models that are showing the population for these 4 countries. So A, also in millions of years, so just like we did for California, because A is in millions and T is the number of years after 2010. So we're going to go through and answer some of these questions really quickly. So what was the population of Japan in 2010? So that one we can kind of cheat on because we already worked out and saw what happened. So the population of Japan in 2010 was how many million people? Yeah, 127.3. And again, the reason being, if we go 127.3 times e to the negative 0.006 and then plug in a 0, this all becomes to the 0 power. So that equals 127.3. E to the 0 is the same thing as 1. So we don't even have to have it there. So it's the same as just 127.3. All right, so the population of Iraq in 2010 was what? 31. Yeah, 31.5. All right, for number 3, which country has the greatest growth rate? And then what's the percentage that they're increasing? First off, which ones are growing? India and Iraq, so those two, because they have positive numbers beside the T. Which one of those has a bigger number? Iraq, right, because we have 0.008, so we're comparing 0.008 and 0.019. The 0.019 is going to be bigger. So we know that it's Iraq that's getting growing the most, or growing the fastest, and it's asking for the rate. What's the percentage? Yeah, 1.9%. Because again, this is just like this sorry, wrong one. Let me keep going up. There we go. Our A equals PE to the RT, where R is our rate, and we put it in as a decimal. So if we're coming from the equation, this 0.019, we're having to take it to a percentage by moving the decimal over by 2. Is that part okay? All right, super. 4, which countries have a decreasing population? Yep, so Russia and Japan. Oh, let me use capitals R. And by what percentage is the population of these countries decreasing each year? So for Russia, what percentage is it decreasing? Yep. And Japan's decreasing by? Yeah, 0.6%. When will India's population be? 1,377 million. So to solve that, what do we do? Almost. We're going to plug that number in where the A is, because that's our final amount. So we're going to take that 1377. We're using India, so equals the 1,173.1 e to the 0.008 t power. Our first step is what? Divide. Perfect. So we're dividing both sides by that 1,173.1. So we've got 1,377 over. How do you not plug it in your calculator? Oh, because it'll be, this one, it'll probably give a rounding error, is the reason I'm not. That's a really good question. So the question was, why am I not plugging this in my calculator and just getting a decimal? Is because you'll start to get rounding errors. So you try not to round anything till the very, very end. Because even if we went out like 4 or 5 decimals, it would start to make a difference. All right, so after we divide both sides by the 1173.1, what do we do next? Natural log. So natural log of all that stuff. So the 1377 over 1173.1 equals, and the whole point, so we can pull this exponent down. So 0.008 t. And then I don't need to put natural log of e again, because natural log of e is the same thing as multiplying by 1. So our last step is, just divide both sides. So dividing both sides by 0.008. And make a little tiny bit more space. So this whole big thing is what t is, and a decimal equivalent 20.03. You guys agree? Super. I'll take your word on it. Thank you. All right, so in about 20 years, to answer their question. We might come back and do 6. How about that? We're going to try and make sure we get through everything, though. All right, half-life. So half-life, a lot of times we'll talk about it with like carbon dating. So they think they can tell you how old a bone is based on how much carbon's left in it, because they know how long it takes for carbon to be depleted to half of itself. So if you started out with 100%, then we'll pretend the half-life is a year. After a year, you'd have 50%. After another year, you'd have 25%. After another year, you would have 12.5%. And another year, 6.25%, and so on and so forth. So we just keep on half and a half and a half and a half every whatever the half-life happens to be. So if you know how much you started with, or how much you should have started with, you should be able to figure out how long something's existed based on how much carbon's left. Bless you. So we'll start with the half-life of a radioactive element, krypton 91. It's 10 seconds. So if 16 grams of krypton 91 are initially present, how many grams are present after 10 seconds? So after 1 half-life, if you start out with 10, what do you have left?
5.
Yeah. So after 10 seconds, we're going to have 5, sorry, we started out with 16 grams. Sorry. However, thank you for listening to what I said. That was great. So yes, we're starting out with 16 grams. So after 10 seconds, we'll have 8 grams left. And after 20 seconds, we'll have how many grams? Yep. 30 seconds. 40 seconds. 50 seconds. Yeah. That okay? So Krypton 85 decays at a rate of 6.3% per year. Find its half-life. So we have what letter? Here, hang on. We'll start out this way. This is where I'm sort of torn about which letters to use. So we have technically this. Right. So technically it's this, but I'm going to actually just write the formula we've been using for money. Because it's the same idea. Okay, it's the exact same idea, but I feel like this looks less scary. So the P is still the initial amount, which is the same thing as the A. The value of the f of x is the same as the accrued amount or the ending amount. And the k is the same as the r, which is going to be your rate. And in this case, because we're wanting to make it not just for money, rate of growth or decay. It's an A naught. So it's A sub 0, like a little baby 0. Yeah, so the A 0 is actually A sub 0, which is red A naught. Again, I think that formula looks a lot harder than it is, because the A equals P, E to the RT is the exact same idea. So if we know, if we want to find its half-life and it's decreasing or decaying at 6.3%, that rate is what? 0.063 whenever we translate it over for the equation. But it's decay, so what are we forgetting? Negative. So a negative 0.063. And then half-life. Okay, well, let's plug in what we know. Sorry, because we're trying to figure out whenever we get to half of it. Yeah, I'm thinking about the bottom one. They're the same, but I'm thinking about the bottom. So we don't know the end amount. We don't know the beginning amount. We know that there's an E, that our R is a negative 0.063, and we have to put a T there because it's asking us for the time. Now, here's the really cool thing. I want you all to pick a different number than what I pick, okay? My suggestion is to pick an even number. If I originally put in 12, then half of it later will be 6. I want you all to pick a different number. So don't pick 12, pick another one. And again, I suggest something even so it's pretty. So if we're going through and solving this with whatever number you have, what's our first step? Yeah, we're going to divide. So by the 12 or the whatever you picked, but divide by that number beside the E. So divide both sides by 12. So we're going to end up with 6 over 12, which is the same as 1/2, which is what you guys should have had. And I need to make just a little bit more space. So we have 1/2 equals E to the negative 0.0636. That's a T. Wow. Yeah, that was a horrible T. T. There. Did you all end up with a 1/2 on the left side? Yeah. Just pick a number. If it tells you half, so half-life, just pick a number and put half on the other side. If it tells you double, pick a number and double it for the other side. And that way it's just nice and easy. You'll get where you're going. All right, so from here, what do we do next? Yep, natural log. Okay, now we're back to good stuff, right? Now it's back to just normal. So natural log of 1/2 equals, and again, I'm going to pull my exponent down, so that negative 0.063t. The natural log of e I'm not going to write. Last step, just going to be to divide by that negative 0.063. And let's see. Did you guys get 11.002? All right. All right, so for C, it's telling us it has a half-life of 4,563 years, and it wants us to find the rate. So after 4,560 years, we're going to have half as much as we started with. So this is where I know their E goes here, and I know it's giving me a time of 4,560 years. No idea what the rate is. That's what they want us to solve for, right? And this is where I'm just suggesting you pick a number. So I'm going to pick 10. So 10 times e to the r times 4,560. If I'm worried about its half-life, other side's going to be, yeah, just a 5. All right, so we're going to divide both sides by 10. And this is where you notice, oh, okay, well, here's that 1/2 equals e to the r times 4,560. Next step, yeah, natural log. So we have natural log of 1/2 equals, we're going to pull this down, so r times 4,560. Natural log of e, same as 1, so we're not going to write it. Last step, yep, just divide. Are you guys seeing that these are the same things over and over again? Yeah. All right, so we technically have r equals natural log of 1/2 over 4,560. I'm going to actually round that up to 2. Is that okay? So your calculator spit out negative 1.52 and stuff times 10 to the negative 4. So your negative 4 means 1, 2, 3, 4, and then fill in those circles. So a negative 0.00015, so I'm going to round it. Is that okay? Did we expect to get a negative rate? Yeah, it's decaying. We expected a negative rate, so that's good. And then it's asking us for the percentage. So this is the rate in decimal form. As a percentage, what is it? So the rate of decay is going to be a negative 0.02%, because we're just bumping it over 2 to go to a percentage. Actually, your homework will probably want this. Probably. But if it asks for a percentage, make sure you convert it over. If it's a money problem, you'll have to convert it over to percentage. All right, but are the steps through this okay? Yeah? Okay. All right, you guys try A. So half-life of aspirin in your bloodstream is 12 hours. How long will it take for the aspirin to decay to 70% of the original dose? There's only one tiny trick on this, and it's not till the very, very end. So it's just wanting to know whenever you get down to 70%. So it doesn't actually care what the original dosage was. It just wants to know if you're going to get down to 70%. All right, half-life of aspirin, again, I'm going to keep, make that capital. I'm going to keep thinking of it in terms of our money, just because I think that's easier to relate to. But that's the same thing. just to make sure we're all aware. Same thing as that. So the half-life of aspirin in your bloodstream is 12 hours. How long will it take for the aspirin to decay to 70% of the original? So we can pick our numbers. So we know there's an E. So we're looking to get to 70%. So we need to get our rate first, right? We don't have our rate of decay. All right, so let's find our rate of decay real quick. We're going to make a note that T is in hours. So normally we've been going through and doing T as years. We'll go through and do hours. We're allowed to. So to find our rate of decay, we're going to pick a number. What number do you like to start with? 4? I heard 4. All right, so after it's half gone, you've got what left? Okay. And then the rate is what we don't know, and it's telling us it takes us 12 hours to get to half. And again, we're doing our T in hours. Is that okay? Yeah, we're going to divide by 4. Perfect. So we've got 1/2 equals E to the R times 12. Next, perfect, natural log. So we've got natural log of 1/2 equals, I'm going to pull this down, so R times 12, or 12R, whatever makes you happy. And then our last step, divide by that 12. So we're getting R equals the natural log of 1/2 over 12. And this is where I'm kind of torn because I don't want us to round. We're going to make a little side note that that's about equal to negative 0.0578. It's about equal to that. No, we'll go ahead and round. I think I'm going to mess you guys up if I don't. We'll try it with rounding. So I'm just leaving it out to 4 decimal places. So I was going to put this in as the rate, but I didn't think you'd like that. So we'll go out 4 decimal places. So now, that was step 1. Step 2. So step 1, we found the rate. Step 2, we're going to use that rate. So we have E to the negative 0.0578. T, because it's asking us how long to get to 70%. Well, I need to pick a number and then put 70% on the other side. 100's pretty easy to take 70% of, right? Or 10, or 1, whatever. We're going to end up the same place regardless. So 70% of 100 is perfect. First step is to, divide by 100. So 70 over 100 is just going to be 0.7. Because it didn't round, or it didn't continue on. So it was a very finite, easy decimal, is the reason I stopped. If it had been something like pi that just goes on forever, I wouldn't have. I'd left it. All right, next step is to, natural log. And we're just going to keep running along the side here. So we have natural log of 0.7 equals, let's pull this down. So negative 0.0578 t, and then just divide. You're saying if it asks for the exact answer? Right, so because I ended up rounding this little guy right here. instead of rounding and putting that for my rate, I could have entered in this whole thing. So we could have written that as natural log of 0.7 over natural log of a half over 12. So we could have done that where the purple would actually be your rate. And that would have been precise. But you guys don't seem to like that. I'm not sure. I know. Ask me again. What was it? Oh, so when we did the natural log of both sides, that negative 0.0578 was in the exponent. So the natural log is only doing the natural log of the numbers down at the bottom or of those bases. And then the exponent travels down in front. So what's really happening, which by the way, this is about equal to 6.17. So what's happening is whenever we do natural log of 0.7 equals natural log of e to the negative 0.0578t. This comes in front using our using our power rule. So we actually have natural log of 0.7 equals negative 0.0578t times the natural log of e. So the natural log is still there, but it's only of the e. And natural log of e is just 1, so we don't worry about it. So for B, a bird species in danger of extinction has a population that is decreasing exponentially. 5 years ago, the population was at 1,400, and today only 1,000 of the birds are alive. Once the population drops below 100, the situation will be irreversible. When will this happen? So it's gone through and it's given you all the information to plug in except for the rate. So we know that we currently have 1,400. So that's our initial amount, 1,400. That was our original amount. How about that? So we had 1,400 to begin with, and now 5 years later we only have 1,000. So E, we don't know the R. After 5 years, we went from the 1,400 to 1,000. Because it's decreasing, the number on the left should be smaller than your A naught, which is that A sub 0 is just your A naught, or your beginning amount. So from here, you're going to go through, solve for your R, and then once you get your R, you're going to set this back up and figure out whenever you get down to 100. I want you guys to go ahead and try it. All right, so it sounds like you guys are getting through the first part pretty easily and then maybe not so much on the second part. All right, so to find your rate, what's the first thing we did? Yep, divide by the 1,400. All right, so I'm going to go ahead and simplify that. It'll be what, 5/7 equals E to the R times 5. Then what do we need to do? Yep, natural log. All right, so this natural log of E is the same thing as 1. We can pull this exponent down as the reason it'll be the same thing as 1. So we have natural log of 5/7 equals R times 5 or 5R. 5R is nicer. I'm just not switching the order to try to confuse you less. And then natural log of E, so it'd be times natural log of E, but we don't need that because times natural log of E is just 1. Okay, so we're to here, and then our last step to solve for R is, yeah, just divide by that 5. So we end up with the natural log of 5/7 over 5 equals R, and that is about equal to what? I'm going to bump it up to 3 at the end. Is that okay? All right, so there's our rate. So step 1's done. Now we need to worry about step 2. So we want to know when we're going to end up at 100 birds. So that's going to be our final amount, is going to be the 100 birds. And then there's actually two options for here. You can either plug in the 1400 from 5 years ago, but you have to remember it was from 5 years ago. Or what I think would be easier, there's 1,000 of them today, right? So if you just plug in the 1,000 for today, then that's going to give you a time that's, from today. So 1,000 birds currently. Then we have E, our rate is at negative 0.0673, and then times our time. So 1,000 is how many birds we have today. And we want to know how long it's going to be whenever we end up at 100. So you could have started with the 1,400, but whatever your time was, you'd have to take 5 years out of that, because the 1,400 was from 5 years ago. If you'd use the 1,400, yes. If you use the 1,400, whatever answer you got for T, then you're going to subtract the 5 years. All right, so what from here, what's my next step? Yep. All right, so we've got the 0.1 equals e to the negative 0.0673t. My next step is going to be natural log. And the whole reason for doing the natural log is so that we can pull that exponent down. So we have negative 0.0673 times t, and then times natural log of e. The natural log of e, same thing as multiplying by 1, so we don't have to put it there. And then our last step is going to be, divide by that rate, or by the negative 0.0673. So 34 point, we'll call it 34.2 equals t. So in 34.2 years, we would expect the birds to be down to 100. Okay, oh, actually this is great. So on your review, number 50, is this problem. And it says round up to the nearest whole number. So it's telling you to go up to the next number. So if it says round up, then we would actually put 35. Because it says round up. If it had just said round, it would have been 34. But because it says round up, it wants you to any decimal makes the whole number go up by 1. The reason being, so we have 34.2. If at 34 years, we're not quite down to 100. And the 100 is the point of no return. Like once they hit 100, they're going to become extinct. So at 34.2, whenever that happens, at 34, there might still be 102 birds or 103 birds. So they're not quite to that point of no return. Right. So, and at 35, you're for sure past that 100 mark, and there's no recovering them. Yeah. Thank you. Very good question. Not always. The problems that we had here for the half-lives, they gave us everything we needed, where we were just solving for t, so it was just one step. And if they were just asking us for the rate, so find the decay rate, same idea. They're giving us enough information, it's just one step to find the rate. But it's whenever they're not giving us a rate, and then they're asking us for some other time. So if they're asking you for rate and time, or if they're just asking you for time but there's no rate, it'll be a two-step. If it says round up to the nearest whole number, then whatever it is, bounce it up like we just did. If it just says round to the nearest whole number, so if it leaves that word up out, and so if it just says round to the nearest whole number, our answer would have been 34. But because it says round up to the nearest whole number, it's going to be 35. Yeah, I know, that little tiny word. All right, so logistic growth model. These are actually pretty easy. This is the same idea. We're just plugging stuff in and crunching through. So here we're given our logistic growth function. F of t equals the 1,000 over 1 plus 5,000 e to the negative, and that's a t. Doesn't look like it, but it is. I'll make it bigger. All right. And this is describing the number of people who have become ill with influenza T weeks after its initial outbreak in a particular community. So for A, it's asking us how many people became ill with the flu when the epidemic began. Well, when the epidemic began, what was your T? What was your time? 0, exactly. I'm extending the division sign. Sorry, I thought it might look a little confusing. So for A, you guys can probably look and tell, but F of 0 is going to be the 100,000 over the 1 plus 5,000, and then e to the 0 is what? Yeah, just 1. So this just becomes what? Just 5,001 on the bottom? Correct, because it's saying whenever it began, so the very beginning. Because it's not an epidemic if like 2 or 3 people are sick, right? Then that's just 2 or 3 people being sick. But once it gets to a large number, it gets classified as epidemic, and you can model its growth. So this was E to the 0 power, and e to the 0 power is the same thing as 1. So it's the same as 5,000 times 1. Does that make sense or no? The 5,001 did come from this 1 plus. But yeah, the 5,000 times e to the 0 is just going to give you the 5,000. So, there you go. All right, so if we put all this in, we're going to end up with, yeah. So 0.99, I'm going to go out 3 places. But really, how many people are we going to call that? Yeah, let's call it 20 people. All right, and then for B, how many people were ill by the end of the 4th week? And again, it told us that T was in weeks. Yeah, so just plug in a 4. And then the limiting size, basically you cap out at some point. What, where you cap out? So we'll determine what it is by putting in a really large number into T. So it's basically whenever T becomes infinity, which I'm anxious for you guys to see. But yeah, so like once T is approaching infinity, which we can't put infinity in, right? So just pick a huge number is my suggestion. And actually we'll probably pick 2 huge numbers, just to double check. So you guys try B really quickly, and if you're feeling brave, go ahead and try C. All right, what did you guys get? Or you plugged all this in? Yeah. And this would be where we would want to see what they asked us to do. If it said to round, we would put 1,080. If it told us to round up, we put 1,081. So it just depends how they asked us to answer for how many people. All right, and then for C, my suggestion is that you just go through and hit the left arrow button to get back into the equation you just entered. And we're going to just pick a huge number. Well, huge is relative. How about f of 10,000? Yeah. So now we go through, and I want to double check to make sure we don't have a, yeah. So it's so close to the 5,000 e to the negative 10,000 is so close to 0 that whenever you put it in your calculator, it's actually just going to go ahead and give you the 100,000. Oops, hang on. There we go. Fixed. So it's going to go ahead and give you 100,000. If you have any doubt, go back in and make your exponent bigger by a number. So if you wanted to make it 100,000 for your exponent, it'll still give you the 100,000 for your output. If you made it 1,000,000, it'll still be 100,000 for your output. If you think about it, so if you have a negative exponent, you guys don't care, but I'm going to tell you anyway. So we're just looking about this 5,000 e to the negative t. Well, that e to the negative t, it's the same thing as 5,000 times 1 over e to the t. Yeah? Okay. Which is the same thing as 5,000 just being divided by e to the t. Well, whenever t is kind of small, like 2, yep, trying to quickly do e squared. It's giving us 7.4, so 5,000 divided by 7.4. Well, then we're going to square it again, and it's going to give us somewhere in the 50s. Or we're going to raise it to cubed instead of squared. But the e to the t is going to grow exponentially. It's going to get huge, really quickly. So whenever we're putting in a really big number like 10,000, so that's the 2.7 and change, 2.78 and change, to the 10,000th power, I don't think your calculator will do it. Okay, I just did to the 100th power. So to the 100th power gave us 2.68 and change times 10 to the 43. So that is going to be basically a 2.6 or 2.7 or a 7 and then 42 zeros. It's huge. Huge. I don't even know what you would call it if you're reading it out loud. So where if you have 5,000 out of again, I don't even know what to call it, but out of a really huge number, you don't care. It's the same thing as 0. But for the most part, it's nothing. If you were to say, well, I know I owe you 2.3 trillion, but here's a penny.